All right. What I want to do next is let's actually look at how small of an increment in amplitude or displacement between max and min the simple harmonic oscillator would have if the spring constant is equal to 10 newtons per meter and the mass is equal to 100 grams or 0.1 kilograms. And so remember we said before it's got restless leg syndrome, it can't sit still. And so what we're looking at here is the vibration that it corresponds to the 0 point energy as we go from plus A to minus A. So we're going to find the value of A that corresponds to this vibration. Okay, so the mass spring system, let's say, is horizontal, and it can't go any lower than this value, which means that it's still moving, even at absolute zero. Okay? And so what we could do then is we could set the energy in general equal to 1/2 k times A squared. So this would be the energy that is associated with the maximum potential energy. In general, this would be plus 1/2 mv squared. So this would be potential energy plus kinetic. But at the turning points, we're going to be going between plus or minus A, and at that point the velocity is equal to 0. So what we have here then is an expression for 1/2 ka squared, which can be written directly in terms of the energy of the 0 point energy. Okay, so we're finding A when n equals 0 for the 0 point energy. We want the amplitude of the vibration when A is the minimum value that it can be associated with the 0 point energy. So what is E naught? That's just 1/2 h bar omega. And that's equal to 1/2 k A squared. Okay, so the 1/2s are going to cancel. So this gives us A is equal to the square root of h bar omega divided by k. But what is omega? Well, omega is equal to the square root of k over m. And so that is from our basic solution of our second order differential equation for a simple harmonic oscillator. Okay, it's equal to the square root of the spring constant divided by the mass, and this is just a classical result here. And so what we can do then is we can plug that into this relationship, and that gives us omega is equal to the square root of 10 newtons per meter divided by m, which is 0.1 kilograms. So that gives us the square root of 100, which is equal to 10, and that would be in radians per second. So that's the value of omega that we can plug in. We know that k is 10 also, and so A then is equal to the square root of h bar, 6.63 times 10 to the minus 34 joule seconds, times omega, 10 radians per second, divided by k, times 2 pi, and k is 10 newtons per meter. So the 10s are going to cancel, and so this gives us then, in terms of a numeric value, the square root of h bar for the amplitude of the motion. Let's see what that is. All right, so that gives us 1.02 times 10 to the minus 17. meters. So this is about 1/100th the diameter of an atom. Or I should say the diameter of the nucleus. So the nucleus of an atom is around a femtometer, which is 10 to the minus 15 meters. So this would be about 1/100th the diameter of the nucleus of an atom. And so that's a fairly small change, one that would be difficult to measure, but still it is not zero. And so that is what is kind of amazing about it. Now, if we were to take the same system and ask, well, what is the n value? What kind of a, if we were looking, say, at a mass spring system like this one, what would be the n value if the amplitude were equal to, say, 10 centimeters? Okay, well, then we could write n plus 1/2 h bar omega. That's our E of n value. It's equal to 1/2 k times a squared. Okay, and so here, n is going to be a huge number in comparison to 1/2. It's going to be somewhere on the order 10 to the 30th power or something. So I'm just going to throw the 1/2 out because it's 10 to the 30th some power plus 0.5. And so this gives us then n is approximately equal to 1/2 ka squared divided by h bar omega. So that would be 1/2 times k, 10 Newton per meter, times a squared, that's 0.1 meter squared, divided by 6.63 times 10 to the minus 34 joules seconds, times omega, that was 10, we got from before, radians per second. And this is h bar, so we put a 2 pi up here in the numerator, like that. And we'll crunch that number out, and I think we're going to find that's a pretty big number. Well, here it's 10 to the minus 34 in the denominator, so that'll flip up to the top. 10 times 0.1 squared can be like 0.1 times pi in the numerator. This is 10, this is 0.01, and that's squared, so that's 0.1. The 2's cancel, so it's 0.1 times pi. So that, I don't even have to punch that part out. 0.314, 1 times pi, divided by Planck's constant. 6.63 times 10 to the minus 34. That gives us 4.89 times 10 to the 31 power. So that's the excited state. Okay, it's on the order of, well, 10 to the 6 is a million, so you'd have a million, 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 million times 10. Okay, that would be the excited state for this mass if it were vibrating at a modest amount that is equal to about 10 centimeters back and